Okay, so for this week, I have a couple of videos for you where we're going to construct parts that contribute to our understanding of the Fourier transform. And I think the first thing that I want to talk to you about is the fact that to do the Fourier transform, I'm going to need a different delta function than I used when I had the Fourier series. And it's one that's a little bit harder to mathematically manipulate. And so I'm going to try to explain why this delta function is useful and how it's analogous to the delta function that we used before. So the delta function that you know is the Kronecker delta, which is the symbol delta sub mn. And what we know about it is that if m is equal to n, then it's 1. And if m isn't equal to n, then it's 0, right? And we really constructed this object because we found that when we had an orthonormal basis, that the combination of the dot product of two basis vectors was either going to be 0 or 1, right? And so we needed a symbol that helped us to understand when this thing was 0 and when this thing was 1. And so we created this delta mn so that way we could have a shorthand for when am I looking at the same basis vector. And of course, using that, it was most useful when I took that delta function and I put or I didn't put it in, but it naturally came inside of a sum, because then as I summed over one of the indices, all of the terms of that sum turned out to be 0, except for 1, right, when m was equal to n. And so this entire complicated sum on the right-hand side ended up just being one number, which corresponded to the one term that wasn't 0. Okay? And so two things to keep in mind from this refresher. One, the Kronecker delta was a useful tool to understand whether or not we were looking at the same basis function, and that it helped us to collapse sums, right? And this was the Fourier trick. It allowed us to calculate those coefficients in something like the Fourier transform, okay? And you're going to use that a lot, especially if you take quantum with me next year. The idea of the Fourier trick and this decomposition is something that we're going to see a lot, and the Kronecker delta is going to be very important to us, I promise you that. But now, when we go to the no boundaries, no rules limit, right, and when we're looking at a function that has no boundary conditions and therefore no quantization condition, then my basis functions are really a continuous set of basis functions, not a discrete set of basis functions. And so I still have the idea of a state, right, which I'm going to call y sub k here. That's the ket form of the state that corresponds to a function, and I'm going to call that y of k, that looks like just one of our bare solutions to the wave equation. It looks like the spatial part of one of the bare solutions to the wave equation. And I've put the normalization constant that we're going to use in there. Perhaps a different Tom would have put something arbitrary, and then we would have solved for it. But you'll see why I chose 1 over the square root of 2 in a moment. Now, the way I take dot products with these functions is going to be exactly the same way that I took them before, except my limits of integration now go from minus infinity to infinity rather than over my domain, because minus infinity to infinity is my domain, right? So if I have two different basis functions, and I'm going to call them just out of convention, I'll call it yk prime and yk, right? Yk prime and yk. And I want to do this dot product, then I have to take the complex conjugate of the first one, right, times the second one, integrated over the entire domain. And when I have two copies of those, I end up with a 1 over 2 pi, right? There's no square root anymore because I have two copies. An integral over dx of e to the minus ik prime x e to the ikx, right? So there are two exponentials here. But when I bring those exponentials together, right, I actually just end up with one term, e to the I k minus k prime times x, and that's being integrated from minus infinity to infinity, right? That's just this dot product. And when you look at this, you say to me, Tom, that is clearly not a Kronecker delta, right? For example, when those two basis functions are the same, right, when k is equal to k prime, that's this case here, then the exponential is e to the 0, which is 1, which I'm integrating from minus infinity to infinity. Well, 1 integrated over an infinite domain is infinity. That is not 1. Okay? This is not the Kronecker delta, and there's nothing I can do about it from that point. But, not all is lost. If I do this integral when k is not equal to k prime, and I'm just doing two silly numbers here, and I'm doing these pretty much because I want you to plug them into Mathematica and see that I'm not lying to you here. But if these two numbers are different, then the two oscillating functions are not the same wavelength, and they end up totally canceling each other out, and the integral from minus infinity to infinity is actually 0. Okay, so it's not the Kronecker delta because it's infinite when I have the same two basis functions, but it's also not the Kronecker delta because if those two basis functions are different, then this product here turns out to be 0, right? And that's one of the basic properties that we wanted. And so the only thing that's going to save us when trying to take the inner product of two of these basis vectors is if somehow that infinity isn't as bad as it seems. Okay, and what I want to try to convince you of in the next slide is that that infinity isn't as bad as it seems because it only exists at one point. Okay, so to understand what I mean by that, let's take this inner product, which is given by this part of the expression here, and let me integrate it over all possible values of k. Okay, and you'll see why I'm going to do that in the next slide, precisely when I do the analogy to the Kronecker delta. But if I think about integrating this over all possible values of k, what I'm doing then is I'm probing all different possible values of k, and one of those values of k will be equal to k prime, and the rest of them won't be. But now I can do the integral over all of those different values of k. And it matters then what the result of that integral is. It doesn't so much matter what the value of the integrand is at one of those points. We've all seen fun functions, right? That when we take their integral, things like discontinuities and things going to infinity tend not to be such a big deal, as long as the volume, as long as the support for that function goes to 0, right? And in this case, even though this structure, that this dot product of two different basis vectors, even though that structure is infinite, it's only infinite at one point. It's only infinite in a very small place. Now, what's lucky is that if I take a course in complex analysis, I can actually do this integral. Okay, it's something that we can do in complex analysis because, or I should say, we can do the whole integral. It's something that I can do in complex analysis, and what I find is that the integral of this weird thing that goes to infinity at just one point, if I integrate it over all possible values of k, then I get exactly 2 pi. Okay, and if that makes you if that is interesting to you, well, stay tuned because you'll probably see it in another course on math methods or in one of your mathematics courses. Okay, but that idea of integrating this thing that's infinite over a small support turns out to be finite. Well, then you're golden, right? Because then I get some number 2 pi, and like we always say, what's a factor of 2 pi among friends? So what I'm going to do is instead I'm going to divide this thing by 2 pi, and then that's going to make this 1, right? And there's the 1 that I need, right? This definition of a delta function that gives me the 1, right? That tells me that I'm only getting one thing out, right? That's the property that I wanted that I wanted from the Kronecker delta to help me understand how the dot product of two basis functions can somehow be normalized. Okay, and so down here I want to bring this analogy back because this integral over k is very much like the sum over n, right? When I had when I summed my when I was doing one of my Fourier tricks and I was summing over n. If there was a delta function on the right-hand side, every term in this sum is equal to 0, except for that one term that happens to be equal to 1, and of course, I get 1. The same thing's happening up here. This structure, right, that I have the inner product of two basis vectors, that structure turns out to be something that's infinite or 0, but when I sum it, right, when I go over all possible values of k, when I integrate it, I end up with 1. And that's a great property. That tells me that I have something that makes sense from a physical standpoint. Okay. And so that thing, now this is the thing that I've circled in red, that's the thing that we're going to call the Dirac delta. Okay. And we're really going to define the Dirac delta to be this representation of this integral. Okay, and you can, there are lots of interesting courses on complex analysis might go further. But whenever we see an e to the I k minus k prime times x, and I'm integrating now over x, right? And that's important here. I'm not integrating it over k. This thing is the Dirac delta function of k minus k prime. Okay? And that delta function is going to be 0 unless k is equal to k prime. It's going to be infinite when k equals k prime. But if I integrate it over k, or integrate it over k prime, I'm only going to get 1, right? And that's the beauty of this particular delta function, is that by itself it looks bad, it looks discontinuous, it looks infinite. But when I integrate it, I get 1. Okay, and in fact, I get 1 in a very special way, because this is one property of the Kronecker delta that I wanted. But there was another property, right? And that was if I take a sum over n, and I have the Kronecker delta m sub n, then this sum is only going to have one term that survives, right? The mth term, right? When n is equal to m, that's the only one that survives. Well, you can see we're going to get the same thing down here, right? As I'm integrating over dk, right? I gotta have my dk here. As I'm integrating over dk, all of these terms, this integral is going to vanish everywhere, right? The integrand is going to vanish everywhere except exactly where k equals k prime. At that point, the integral of the delta function is 1, but it's being multiplied by the value of this function here, right? 5k. Right, so this integral is 1. Oops, I don't know why I erased that. This integral is 1 times the value of the function at that point, which is the function evaluated at k prime. And this analogy here should be perfect, right? Because the m and the n. So up here I'm summing over n. Down here I'm integrating over k. The a sub n's are the phi sub k's, or the phi of k's, right? And when I do this integral, I'm summing up, if I think about it as a Riemann sum, I'm summing up over all of the points, over all these tiny little intervals, until I get to that one interval where the delta function isn't 0, and therefore the delta function returns an integral of 1 times the argument of the function that it's being multiplied next to. And that's why the only thing that survives at the end of the day is the k prime. The way in the top, the only thing that survived was the m. And that's why a lot of people will say the delta function, the Dirac delta function, isn't a function, because it doesn't make sense by itself. It's really a functional, in the sense that it makes sense once I integrate it with another function, right? And in the previous slide, that other function happened to be the function 1, evaluated everywhere. But this is why a lot of people will insist that you call this a functional rather than a function. Okay, so now I can get back to the problem at hand, which of course was decomposing phi of x in terms of this set of basis functions, which we called y of k, right? So the problem that we have when we want to do a decomposition like this is to find out what are the expansion coefficients, right? What function here multiplies by my basis functions to give me my original function back, right? And we've talked about why this phi of k has to be a function and isn't just a set of coefficients. Well, I'm going to do the Fourier trick. I'm going to multiply, and I did this in green, right? I'm going to multiply each term by the complex conjugate of another member of the basis functions. So 1 over the square root of 2 pi e to the minus I k prime x times phi of x. That ends up being multiplied on the right-hand side. I've tried to keep the color coding here so that you can see everything I've multiplied on the left in green is being multiplied on the right in green. I've just split it up into different points. And so in the bottom line here, I see that I clearly have this integral, this green integral, right, which is just a delta function. So I can replace this whole thing with the delta of k minus k prime, and then I can do the integral over dk, and at the end of the day, I get out phi of k prime, and therefore I can solve for this function phi of k prime. And I get that it's equal to this thing on the left-hand side here, right? And so this looks so much like the Fourier trick because it is the Fourier trick. I've been able to solve for those coefficients by doing this integral over the left-hand side, right? Which is exactly what I did, except now this thing is a function of k prime rather than being indexed by, say, n or m. And so if I rewrite this, I'm gonna do that algebra that I did at the bottom of the last slide, but I'm gonna do it a little bit. I'm gonna do it in one little pretty line that you can always remember. The left hand side just stays the way it is. That's the integral that I have to do. The right hand side, I'm imposing the delta function, and I end up with just phi of k prime. And this defines the Fourier transform. Of course, the physics of the Fourier transform is for our next video. Now, the last thing I want to say is that both delta functions in this course have the same purpose, right? They both aim to allow us to do the Fourier trick. They allow us to solve for those coefficients so that we can break up a function into the eigenstates of the problem, that we can break up a function into the functions that naturally define the problem. And we have a definition now of what it means to be a delta function, and we have the usefulness of it that when I take a delta function and I integrate it over the domain, it allows me to extract the value of the function, but just at one point. All right. Good luck with that. See you soon.